All right, for those of you who were here at the Phobos and Deimos workshop, I'm afraid I didn't get any new breathtaking results since Monday, so this talk is going to be broadly similar to whatever I talked about on Monday. But yeah, this is just to present some work in progress of this project we've been working on with Robin Knopf in the last couple of years on trying to form Phobos and Deimos via an extended disk around Mars. Next slide. So just to a brief overview of some of the parameters. Is there any way to play this on a PC rather than a Mac, or? Okay, well, all right. Well, I apologize for the disturbed sign. Um, so Phobos and Deimos have very small masses of the order of 10 to the minus 8, 10 to the minus 9 times the mass of Mars, and very small densities. An interesting, very fundamental characteristic of the system is that Phobos is inside co-rotation that we can find at about 6 Mars radii, while Deimos orbits outside. And while Phobos is today around 2.8 Mars radii, if we integrate back its orbit for about 4.5 billion years, we think that it was actually orbiting much closer to the synchronous orbit, maybe around 5.5 Mars radii. Next slide. So as Pascal mentioned, the origin of these two objects remain highly uncertain. The intact capture has been argued mainly for spectroscopic signature of these objects. However, it seems difficult to reconcile this theory with their current equatorial orbits. So instead, it's been suggested that they could have formed in situ from a disk, mainly by Craddock in 2011, who said that a giant impact on Mars could produce a disk. However, we want to point out that impacts that produce very low mass disks would not place material into extended orbits close to where we find Deimos today. Rosenblatt and Charlotte in 2012 studied the evolution of a low-mass compact disk and showed that it could spawn transient moon, but that would eventually be lost due to inward tidal evolution. Since 2014, we've started exploring the alternative of forming Phobos and Deimos from a massive extended disk whose outer edge extends around 7 times the radius of Mars. Next slide. So what are the requirements for such an origin? We need a big impact. There's clues to big impacts on Mars. Its 25-hour day implies an impact by an object that was roughly a few percent the mass of Mars. And also Borealis Basin have been generally advocated to be the signature of a large impact on Mars. This large impact is going to produce a disk whose mass is much larger than that of Phobos and Deimos. This is not a problem, as we expect all the material that could be found inside the orbit of Phobos initially would tidally decay and fall onto the planet. We need an outer disk edge that's going to be near Deimos. So we need material that is initially outside the Roche limit. but we do not want to have a disk that extends significantly further the orbit of Deimos, as it would have likely accumulated in other satellites that we don't find today. And so in this framework, Phobos and Deimos are the sole survivor of a once larger satellite system around Mars. Next slide. So we started by performing a number of SPH simulations to see with the disk that could come from a giant impact on Mars. We performed roughly 100, 500,000 particles SPH simulation, and we considered two types of impact. One that we qualify as large, where the impactor is about 3% the mass of Mars, with a relative low velocity. These types of impact would be capable of producing both the rotation of Mars as well as the Borealis impact basin, if we follow the requirement for Marinova et al. And we look at another type of impacts that we call smaller, where the impactor's mass is about 0.3% that of Mars, and at a higher velocity. And these are the type of impacts that could be capable of producing the Borealis basin if we follow the Nemo et al. Estimates. Next slide. So I'm going to show you a typical simulation from an SPH impact. This particular simulation uses an impactor that's 3% of Mars's mass, so it's in the large regime, at a 45-degree angle and an impact velocity similar to the escape velocity. Next slide. As the object collides with Mars, it heats up the target and ejects material into orbit. The different colors here represent different temperatures, and we are able to, in this particular simulation, to account for the rotation of Mars in a pretty good agreement and form a disk whose mass is about 9 to the negative 4 times the mass of Mars. And we form a disk that has roughly 300 particles so that we marginally resolve its structure. Next slide. So this is a representation of the impact outcome based on our 100 simulations. On the left, we show the disk mass in units of the mass of Mars as a function of the scaled impact parameters. The different colors represent different impact velocities. The circles are for the large objects, large impactors that contain 3% of Mars's mass, and the triangles are for the smaller objects that contain 0.3% of Mars's mass. And we form disk masses whose masses range roughly from 10 to the minus 5 to maybe 10 to the minus 3 times the mass of Mars. And on the right, we show the disk radius in units of Mars radii as a function of the disk mass. And we find that, again, for a wide range of impacts, we are able to place material into orbit close to the orbit of Deimos here around 7 Mars radii. Next slide. So next up, we look at the evolution of the circum-Mars disk using a hybrid disk model that we primarily developed to study the accretion of Earth's moon from the prolunar disk. This is a hybrid modeling in which we model the material inside the Roche limit here at 2.7 Mars radii by a uniform fluid disk that spreads viscously, and the material outside the Roche limit by a collection of several thousand individual moonlets whose orbital evolution is tracked with the antibody code SIMBA. The synchronous orbit here is at 6 margin radii, and because we include the effects of tidal evolution, the objects inside the synchronous orbit are going to be pulled in toward Mars, while those orbiting outside synchronous orbit are going to be pushed away. And finally, we include the interaction between those moonlets and the inner disk at Lindblad resonances, which is going to push these objects away from Mars. Next slide. So there's going to be an interesting competition between the disk torques and the planetary tides. We expect that satellites will grow from accumulation of the material initially in the outer disk. The disk torque will tend to push these satellites away. We point out that once an object reaches about 4.2 margin radii, all of its first order Lindblad resonances will be outside of the disk, so it will not be pushed away directly further by the disk. However, if it captures an inner object into a mean-motion resonance, and that inner object is itself being pushed by the disk, then in turn that outer objects will be pushed away to larger distances. Conversely, the tides will tend to pull these inner satellites inward. So what will be the balance between the disk torques and tides? That will depend on the current Mars tidal Q, which is of order 10 to 100. Our concern here is that if the inner large moons that would form in the outer disk significantly migrate away, they may perturb the region where Phobos and Deimos may have originated and potentially accrete or scatter the objects. Next slide. So this is the representation that I will be using in the next few slides. On the x-axis, you have the semi-major axis of the orbiting bodies, and on the y-axis, you have the mass of these bodies in units of Mars's mass. The orange slab here represents the inner disk, whose mass is 10⁻⁴ in this particular simulation. And this curve here represents the total mass in the outer disk in bins of 0.1 margin radius. As you can see, we use a surface density profile that decreases with distance. Next slide. So we first start by looking at accretion from a massive disk. This is a disk that contains about 10⁻⁴ Mars masses. We put about 10% of the mass in the outer disk, and we use a tidal Q that's fairly strong, of about 15. Next. And as you can see, we form very rapidly some very, very big objects inside in the outer disk. And these objects are so big that the feeding zone extends all the way beyond the synchronous orbit, and they end up eating all the material initially present in the outer disk. They eventually totally decay into towards the planet, at which point they get totally destroyed and replenish the inner disk in material that the disk eventually spreads back and starts forming a secondary set of satellites that cannot move away very far because of the strengths of tides and because they cannot move away further than 4 point something Mars radii by direct interaction with the disk. Next. So we'll start looking then at a disk that is less massive. This simulation has a disk that is 10 times less massive than the previous one, with a similar mass ratio, 90% of the mass inside the Roche limit and 10% outside. And we use in this particular simulation a lower tidal Q, so a weaker tidal dissipation to Mars. Next. And so again, the objects accrete, and we form two good candidates for Phobos and Deimos equivalent objects, but because tides are weak, the objects inside the orbits are able to move away and accrete the material that Phobos equivalent. And eventually, because that object is going to is farther away, it's not interacting with the disk, but it's capturing inner moonlets that are themselves interacting with the disk, and they're being pushed away, and eventually they end up destabilizing Deimos and capturing it. Next slide. We can see this a little better in this on this couple of graphs. On the x-axis, you have time. Here on the upper graph, you have the distance. The different black curves show the evolution of the semi-major axis of different satellites in the simulation. You have here body number 4 that is merging with body number 3, and when that happens, it ends up losing angular momentum. Its semi-major axis contracts, and it hits the 9.7 mean motion resonance with body number 2. It's being pushed away by the disk, and in turn, it's pushing away body number 2 due to the resonant configuration. And eventually, that body is going to hit the 3:2 mean motion resonance with our Deimos equivalent, at which point Deimos's eccentricity gets highly excited due to the resonance configuration, and it ended up colliding with body number 2 after a few million years. Next. So in this last simulation, we use the same disk mass, but we crank up the tidal dissipation into Mars to the higher end of the strengths that we can expect. Next. In that case, we again form big satellites inside, but because the tide is this time stronger, there's no substantial outward evolution of these moonlets, who are then quickly lost due to inward tidal evolution, and we're left with two objects, a good Phobos and a good Deimos equivalent, that are not perturbed, even though eventually the disk spreads back to the Roche limit and start producing a second set of satellites that cannot move away very far due to the strength of tide, and the two Phobos and Deimos can be preserved. Next. So this is my last slide. So in summary, we find many impacts compatible with Mars's rotation that can form extended disks. We're going to need higher resolution runs for SPH simulation to perform, to explore less massive disks. We find that formation of Phobos and Deimos seems to require strong tides and a slightly smaller disk mass. But we also point out that we find many cases if tidal dissipation in Mars is weak, or if we have a very massive disk where Phobos and Deimos